mesmo assumindo a supergravidade, a supersimetria e a supergravidade. Best. So, on the first part, we made a transition. We went from taking the metric as the most important thing to regarding the field bind as the most important thing. And actually, we transformed this field bind into a one form, into a collection of one forms, or more precisely, into a Lorentz vector of one forms. I don't know if you are familiar with the Pauli matrices. Many times people write them as a vector. And they think of it as a vector of matrices. This is a vector of one form. Well, once we get a one form, the first thing you have to do is take the exterior derivative.
Say, sorry?
The exterior derivative.
Oh, yeah.
According to the definition, the exterior derivative of the field bind, the one form field bind, is this. It's a two form. And we can be a bit more explicit and perform this anti-synchronization in the indices. And this brings in a factor 1/2. Okay. So these are the components of the two forms exterior derivative of the field bind. Now this two form also has one index, one Lorentz index. So a natural question is, does it transform as a Lorentz vector? Because we know that the field bind transforms as a vector. But what about the derivative from the field bind? I wouldn't be posing the question if the answer were yes. So actually the answer is no, it doesn't. Why? It doesn't because these Lorentz transformations are local. They depend on x. And so they have a non-zero derivative. So let's take a look at it. So it's the, I will be a bit more explicit. So if I make this change in the field line, the derivative of the field line also transforms, but transforms in a way that it's non-homogeneous. Because as you see, it's not simply that we take this matrix and we multiply it by the derivative of the field line, but we also get this non-homogeneous part.
Still one form vector.
Say it again, please.
The transformed field line is still a one form vector.
Say this.
Yeah.
This is still. This is a zero form. So this is still a one form vector. This is a two form, but it has one index. So you would expect to transform as a Lorentz vector with one index. But it doesn't. It doesn't because the transformation is local, and so we get this non-homogeneous term. So this is quite like in gauge theory, Gangren's theory, when you have that it's not necessarily a spinor, but okay. This terminal field transforms with a phase. But the derivative has a non-homogeneous part. Are you familiar with this? So it's the same kind of situation. You have a field that transforms in a certain way. In this case, it transforms with a phase. But the derivative of the field does not. There is a non-homogeneous term here that comes about because the phase is not constant, it's x dependent. So it's exact the same situation here. So do you recall how you can solve this problem there and get something that transforms in the required form with a phase? Here we define what is called a covariant derivative. when you introduce a new vector that has to transform in some particular way to ensure that this covariant derivative transforms with a phase. So, and this requirement fixes the transformation law for A. Have you seen this in your lectures? Okay. So we will take a similar approach here. We're going to introduce a covariant derivative that we will demand transform as a vector. And this will tell us, this will introduce a new field, like this A, and this new field will have specific transformation laws so that the covariant derivative does what we want it to do. It's called the Lorentz covariant derivative. And we will use a capital D. And if we apply it to the field line, for instance, it will be the old derivative plus a one form with two indices times the vector. So it's a matrix times the vector. And this one form here, it's the one form Lorentz or spin connection. That's how it's called. And I'm doing a slight trickery here because this is a one form. This is also a one form. So the product between them is a wedge product. But I'm not writing the wedge. It's just notation. Function. But it's no problem because they are differential forms. There's only one way to multiply differential forms together, and this is the wedge product. So every time we multiply differential forms, we are assuming that it's a wedge product. Well, the thing we want to happen is the following. We shall demand just like that. By definition. And this means that we will have to compute the transformation law for omega in such a way that this is fulfilled. You follow me? Yes, sir. Any questions, please? Well, so we will actually write down this equation in detail and isolate this omega. So here, the prime version of the covariant derivative is d e prime a plus omega prime e prime I'm writing down this equation. Here the prime version of the covariant derivative. Here the without prime. And now I know what E prime is. But I don't know what omega prime is. E prime again is here I use Leibniz rule. So it's a bit of a mess, but we'll sort it out. This term is repeated here. And all the other terms share a field line. Here, here. And of course, this equation has to be valid for every E. So we can factor out the E in this way. You have to be careful with the indices because here it's EC, here it's EB, but it's no big deal because we can change here. Instead of B having C, it's a dummy index, so no problem. And what do you get? You get so now all we need to do is to isolate the omega prime, and to do this we need to multiply by the inverse of this matrix here. So maybe it's easier if I do it in matrix language. We have V lambda plus omega prime lambda equals lambda omega. That's the equation here without the indices, because everything has two indices, so it's like a matrix. To isolate this, we need to multiply by. So what we get? That's the transformation.
How do you take the external derivative of the zero form?
It's the partial derivative. Well, it has two indices. Actually, the inverse if you are very careful with the position of the indices, you can show that the inverse is like this. So we can restore back the indices here.
Sorry, I didn't understood your question. What's the difference between the exterior derivative from the one format to a two form? It's nothing. You just apply for an infinitesimal element and have it as partial derivative.
Well, yes, but if this is a zero form, so it doesn't have mu indices.
Okay.
So you don't have to antisymmetrize anywhere.
You don't have to?
Antisymmetrize.
Ah, yes. Okay, okay. No. Thanks.
But I erased it. But if it is one form, for instance,
Okay, sure.
then you have to perform the antisymmetrization.
Okay.
So this is the transformation law, omega. And as you see, this part here is the homogeneous part, which is what you expect of a tensor. A tensor transforms like this, multiplying matrices. But it has a non-homogeneous part as well. And it has to have, because we want this full combination to be a vector. But this is not a vector, and so this can't be a tensor. But out of non-tensorial components, we build a tensor. So this is actually a transformation law of a connection. This is a non-abelian gauge transformation. I don't know if you can cut the word there, but so that's the definition of the covariant derivative, the Lorentz covariant derivative. And you can use it for any vector, for any tensor. For a vector, it's the same thing as the field line. For a tensor, if you have theta AB, it works like this. So you have correction terms for every index. This has one index, one correction term. This has two indices. There are two correction terms. The first one has a plus because it's correcting an index that's up. The second has a minus because it's correcting an index that's down. It's very simple. And this, the exterior covariant derivative of the field line is called torsion. Definition. And it's a two-form, which means it has hidden indices. It's a two-form, so it has two more indices that we are not writing down. And yet it has three.
I do not understand that form.
Because the field line is a one form. If you take the exterior derivative of the field line, it becomes a two form.
No, yes. All the two forms have these forms.
Yes. Every two form
Because you only wrote the form for the field line. The differential form is the name.
yes.
The differential form for the field line, and when every I don't know how you call it. The three form will have three differentials
Yes.
multiplied.
Yes. A P form, you usually write it like
Okay,
this.
I remember now. The form. The gender. Oh, okay, I forgot. Sorry.
No, it's okay. More questions? It's okay? Okay, so from the field line and this covariant derivative, we build up the torsion. And torsion is a Lorentz vector by definition, because that's how we build this covariant derivative. So it transforms as a Lorentz vector. So now we will play a game. We will keep taking covariant derivatives to see what happens. You know the exterior derivative squared is 0, but that doesn't imply that the covariant derivative squared is 0. This is not true. So we will show how it works. By definition, this is a Lorentz vector. So the definition of covariant derivative says we have to do this. Just as with the field line, same thing. But now we will here write what is the torsion. The torsion is the covariant derivative of the field line. So I'm going to apply this exterior derivative here. So here squared is 0. And here I have a product. So I have to apply Leibniz rule. So it's the derivative of the first and now this d will jump a one form. So it turns out a minus sign. That's what the Leibniz rule says. And here, I just complete. And you see that this minus sign is very important because this term cancels with this term. And so there are no derivatives of the field line left because there is no second derivative and there is no first derivative also. And all we get is the following. I'm going to factor out this field line here and this guy there. So that's our result. So if we take the exterior covariant derivative of the torsion, that is the second covariant derivative of the field line, the result is a tensor times the field line. There is no derivative of the field line anywhere. It's completely algebraic. Now, this is a vector. This is a vector. Omega is not a tensor, but this combination here has to be a tensor. It has to be a tensor because this is a vector and this is a vector. And the only way we get a vector is if this is a tensor. So that's your second homework. And we will give it a name here. So you have to use the transformation law for omega, this equation here, and show that all these derivatives of lambda cancel, and you are left with the transformation law for a tensor, which should be only this part, without a non-homogeneous term. That's the homework. This is called the curvature. And it's a two form, so the same as the torsion.
Sorry. This two connection was generated when we constructed the covariant, Lorentz covariant derivative. Okay. But I can. Why is the curvature?
Oh, we will show it.
Oh, okay.
It's not trivial.
Sorry.
It's, yeah. So far it's just a name.
Okay.
We'll show. Actually, you will show. You, I mean, plural. So you see, this is a two form that has two Lorentz indices. So when you write it down, it has four indices in the end. The two original ones plus the two, because it's a two form. So it has four indices. This is actually the Riemann principle.
You can say that this is a different kind of contraction.
This is a different way of studying differential geometry, actually.
Of what?
Of studying differential geometry. It's called the first order formalism. And it's nice because it's very similar to non-abelian gauge theory. So, we started with the field line. We took its covariant derivative and found the torsion. We took the covariant derivative of the torsion and find that it can be written like this. So, of course, we will take now another covariant derivative, but this will be the last one. Okay? You will see why. Let me see the last thing. It's an exercise. I'm not going to show it, but it's true. Anyone that defines some kind of derivative that does not satisfy Leibniz's rule is crazy. So we're going to apply this covariant derivative here, and we're going to use Leibniz's rule. And this is what we would get. I'm going to write it down here. What sign do I get here? Plus or minus? I'm using Leibniz's rule to take the derivative of this problem.
This is a 3 form or 2 form?
This is a 2 form, this is a 1 form.
So it's a 3 form, the derivative.
Yes, but the whole object is a 3 form.
The object. So the derivative of the object, that's a 3 form, is
It's the derivative of the first times the second, and now comes a sign. It can be plus or minus. In this case, it's plus, because this is a
This is
two-form.
minus 1
Because
squared.
I guess a minus 1 squared.
Yes.
But this is the torsion. So we actually, what we need to compute is this guy. Because here we know what it is. So we need to compute this guy to find out what this is. And the definition says that's for any tensor. So this would be a bit long, but hopefully we will come out. This is by definition, and now I need to introduce there this thing, the definition of the curvature. Okay. Let's see. So I replaced this R with its definition. It's d omega plus omega squared, basically. Yes. Okay, so now only a bit of patience. Here it's d squared gives 0. Leibniz rule here. This is a one form, so I get a minus sign. Here I multiply. I hope everything's okay. Please check, don't just copy. Because it's very easy to make a mistake. There is a mistake
No, it's
here.
omega, yeah, it's B.
Yeah, it's big.
That's correct.
We go on. There are two kinds of terms. This is d omega times omega, and this is omega cubed. 3 omegas. So let's see. If I change the order here, this is a one form, this is a two form. So it's minus 1 to the power of 1 times 2, that's plus 1. So here, I don't have color chalk. I'm going to change the order in this term. So it will be minus d omega AC omega CB. You see? I interchange a 1 form and a 2 form. And there is no sign change because one of them is a 2 form. And now this is identical to this, with the opposite sign, of course. So they cancel. These two here, they are already identical. You see? So they cancel. And here, I'm going to take this 1 form and interchange it with this 2 form. 1 form, 2 form, interchange. There's no sign change because one of them is a 2 form. So I get minus omega A D omega D C omega C D. That's the interchange.
The sign is determined by the larger.
No, but whether one is even.
Whether.
This is the rule. A P form, a Q form, if you interchange them.
Oh, right.
So if one of them is even, then it's a plus. It's only minus if both are odd. But now you see this is identical to this. The name of the indices is changed, but those are dummy indices. The important thing is the order in which they are contracted. First one is A, last one is B. That's correct. Then this goes with this goes with this. Same thing here. First one A, last one B. This goes with this goes with this. Opposite sign. So this is C. If you didn't follow all the details, you have to do it back home. Okay? Because it's very important to get used to all these manipulations that you interchange one form and two form, and you change the name of the indices, etc. Okay? So this is 0. And if we take another covariant derivative, then we will get 0 here plus the derivative of the torsion, and we don't generate anything new. We start repeating. So there is nothing left. That's all there is. So we take as this one, these two we will take as independent. We don't know what they are. But from them, we build the torsion and the curvature. And these two satisfy two identities. If you take the derivative of the torsion, you get this. And if you take the derivative of the curvature, you get 0. These are definitions. These are identities. These are called the Yankee identities. And all these equations put together sometimes are called the Maurer-Cartan structure equations. Okay, that's a mouthful. This is what mathematicians call a free differential algebra, which means it is a set of differential forms that you can multiply together, you can take the derivative of them, and you never get out of the set. It's closed. Closed under the action of the exterior product and the exterior derivative. So it's like a complete set of fields to describe geometry. So it's the same formalism of Riemann for differential geometry, but in a new dress. This work by Cartan. That's the guy who invented all this. This guy. French mathematician, Élie Cartan. Cartan had a long discussion by letter with Einstein, which involved torsion. Because in Riemannian geometry, you usually assume that torsion is zero. And in general relativity, you usually assume that torsion is zero. And Cartan says, okay, well, torsion is a natural element here. It just appears. You cannot set it to zero arbitrarily. If you do it, there must be a reason. And Einstein said something like, okay, who cares? Nature doesn't seem to have torsion. general relativity works that way without torsion, why bother? But in principle, it should be there. And there's still no good answer to that. No one has measured whether space-time has torsion or not. But people think that it should be important because spinor fields should be a source of torsion, in the same way as boson fields are a source for curvature. So that's more or less the idea. Okay, so this is equivalent to the usual formalism, so you can show equivalence. In particular, you see torsion is like this, the curvature is like that. So this is equivalent to the torsion tensor. And here you have a Lorentz index, and here you have a space-time index. So to transform one to the other, you use the field line. This is E A lambda and the Riemann tensor that's how you transform from one frame, these two indices, again the orthonormal frame. You use the field line and the inverse to transform to the coordinate places. But to really show the equivalence, you know how to build up the metric. The metric is like this. But what about this guy? That's the Christoffel connection. And this equation makes the connection between the two worlds. This is like a covariant derivative, but it's kind of a crazy covariant derivative because you use the omega to correct this latile index, and you use gamma to correct this space-time index. and you set it equal to 0 arbitrarily. But the thing is, from this equation, you can isolate the gamma, and you can show that the torsion and the Riemann tensor are equivalent to this, when the torsion, of course, is I hope it's correct. I'm trying to remember the definitions. This is the usual definition of torsion and curvature, the Riemann tensor. And these definitions are equivalent with these ones if the gamma is taken from this equation. That's how you show the equivalence. And that's your homework. That's not so easy. It's kind of easy for the torsion. That's 3 lines. For the Riemann curvature, you have to be a little bit. You have to know the answer. and then you see, if I combine this with this, then it will come out the way I want. But without knowing the answer, it's very hard to. But it's possible. I did it once. Questions so far? Is it okay?
You're still going to talk about the geometrical interpretation of the torsion. You're still going to talk about the geometrical interpretation of the curvature. Because the math science for me is perfect, but it's really hard to see that as a curvature tensor. You know, what torsion is going to do with space time.
Yeah, I understand. It's not easy to come with an example that shows very clearly, but for the curvature it's kind of easy, but for the torsion it's not so easy. You have to think of a surface which is a little bit like staircase. This kind of revolving staircases.
Okay.
These have non-trivial torsion. This is a space with non-trivial torsion. It kind of goes around itself. No, what I just showed you is formalism to deal with differential geometry, the tools. Now you might want to do something with those tools. And this something we will do in the time we have today is how we build general relativity with this. How we write up the Einstein-Hilbert Lagrangian and the Einstein field equations in this format. So I will give you the answer, of course, but then in the next lecture we're going to discuss a bit why it can't be anything, why it has to be something else. We need a Lagrangian. Because usually what you do here is you build up an action, which is the integral over all the space-time of a Lagrangian density action. That's function of the fields and the derivatives. And you compute the variation of this and you get field equations. Now, you have to integrate over all space-time. It's a 4-dimensional integration. And differential forms are just built for that. Differential forms are built to integrate. They come ready to integrate because they have the differentials. You see? So, if you're going to build a Lagrangian, it has to be a 4 form. So that's the first thing. We have to build a 4 form using those ingredients, using the curvature, the torsion, the spin connection, and the field line. That's what we got. And whatever we build, it has to be Lorentz invariant. Because we only care about things that remain invariant under these local Lorentz transformations. The metric, for instance, remains invariant. Gauge invariance. And the ingredients we have these are our fields, these are the derivatives, and we have the eta AB, and also this Levi-Civita tensor to contract indices. So I want you to think a bit about how can you build a 4 form, multiplying these things in such a way that the result is Lorentz invariant. How can you see that it's Lorentz invariant? Because it has no free Lorentz indices. For instance, if you take this and you contract with itself, there are no free Lorentz indices. This is the contraction of two Lorentz indices, you can write it like this. So it's a scalar. It's invariant under Lorentz transformations. And this is actually a 4-4. So this is a candidate. This has all the requirements we need. But can you think of another one? Hmm?
Curvature is scalar.
But how would you build it?
The product. It's not a true form.
This is a 2-form.
The product with itself.
Okay, for instance, you could do RAB or like this. I wrote the indices like this because you have to contract them all. You're not allowed to have 3 indices. This is a 4-form, and it has no 3 Lorentz indices, so it's okay. This is another candidate. Can you think of another one? There are so many.
All the combinations of products of two forms with two forms.
For instance, this is a 2-form, this is a 2-form, but if you multiply them, there's always going to be a 3 index. So it doesn't work. But what else can you do?
Omega and R.
Omega and R?
Yeah.
It's a
So it would be a
3-form.
3-form.
Oh yes.
Omega is dangerous because omega is not a tensor. So even if you do this, for instance, this is not guaranteed to be invariant because you're contracting indices, but this is not a tensor.
And with a curvature.
If you
The both with the curvature. It's a 4-form. I don't know if it's
which one?
two omegas and one R.
Yeah, but omega is dangerous for this reason.
And two E's and one R.
2 E's and 1 R, that could be RAB.
You can have one E and one T because you. It's a
If you multiply
3-form.
this, that's a 3-form. It's like a Lego puzzle. So we're not using omega explicitly. It's implied here. It's implied here. Can you build a 4-form using the epsilon to contract indices?
The epsilon is a 0 form.
It's a 0 form, yes.
Epsilon RR.
Like this? That's a good candidate. It's a 4-form and it has all indices contracted. Can you think of another possibility like this?
The obvious one.
T A. No, T E T E. Combination between T and R.
T and E?
Yeah.
That
Together
gives
with
a
epsilon.
3-form.
But yes.
EET with an eta to contract the remaining
You see
index.
T,
E with an eta
but
contracts the remaining index.
no, but you always have a free index. For instance, you can contract there, but you get a free C. With epsilon, use the Levi-Civita.
T, and an eta.
Epsilon, T, and eta. Like this?
Yeah.
That's 0.
Oh, yes. But it's still scalar
It has all the requisites. It's a scalar, it's Lorentz invariant, it's a 4 form, but it's 0. You see why it's 0, no?
I
It
know.
has epsilon in it. Yeah.
It's not. Another one. And it's also 0 because if you interchange the torsions, there are 2 forms, so this is symmetric in AB.
Yes.
So it's also 0 when contracted like this. Come on.
Epsilon E.
Like this?
Yeah.
That's a good one. 4 form, no Lorentz synthesis free, it's invariant. Another one?
Epsilon R E.
Epsilon R E, like this? That's another one. It's a 4 form, it's 2, 1, 1, no free indices, so it's a scalar, it's not 0. Actually, I don't think there are any other. That's all there is. And these 3 here they're very similar, you see. Here you have epsilon and only e's. Here you take away 2 e's and you put an r. And here you take away 2 more e's and put another r. This is a family of Lagrangians. This is called the Lovelock family.
The what?
Lovelock,
Lovelock.
after David Lovelock. If you want to look at the source, it's That's the original paper. But the paper by Sumino, it's much more easy to read. Now, one of these three, it's the Einstein-Hilbert Lagrange. Which one would you guess?
It's the last one.
No, it's not. It's not because this has R squared. The Einstein-Hilbert Lagrangian has only one R. It's linear in the curvature. So it's actually this one. I was saying that this is the laptop family in 4 dimensions. There cannot be more, you see. This is only filled by this.